In an ideal filter, the power transmission coefficient, ideally has a value of 1 for every frequency within the passband. But we just saw that making a filter of that perfection is not possible with a finite number of elements, a finite order. So at the very least, we would like, ideally, the transmission to be uniquely a value of 1 at least one frequency within the passband. For most filters that we talked about, things like Butterworth, elliptical, the value of transmission will be 1 exactly at the center of the passband, at the center frequency. And this is the ideal case. Now, for some Chevy-Chev filters, that might not be the case because of the ripple, but at least there's some frequency, at least one frequency, where ideally the transmission is equal to 1. The reality, though, is in real filters, if we build them and test them and such, that we find that there really is no frequency where the transmission will be exactly equal to 1. We'll find a frequency where the transmission will be its largest value of any within the passband, and oftentimes that is the center frequency. But the value of the transmission, the power transmission function at that center point, will be something a little bit less than 1. So why is that? Why is the transmission slightly less than 1 for real filters that we can construct? Remember, there are two assumptions that we made about microwave filters. We first said that microwave filters ideally are lossless, and likewise microwave filters ideally are perfectly matched within the passband, or at least at one point, one frequency within the passband. Of course, getting that level of perfection is never obtainable. What we find is there's always going to be a little bit of mismatch, even if it is very well matched at the center frequency. The input impedance will never be precisely equal to 50.000 and so forth ohms. And likewise, what we find is the idea that our filters are lossless is not exactly correct either. Certainly we build our microwave filters with reactive elements, or try to. Inductors, capacitors, distributed elements, links of transmission lines, lossless transmission lines, resonators that are ideally lossless. But of course there's no way we can construct these filters out of conductors that are perfectly conducting. There will always be some resistance, and also the insulators, dielectrics, they are not going to be perfect either. There'll be some level of conductivity, and because of that, there's an ability for those materials to absorb energy. In other words, even though our filters are very low loss, they are not completely lossless. And so there'll be some amount of energy, electromagnetic energy, that is absorbed as it passes through the filter from one side, from the input to the output. So to the extent to which the input port is matched for a frequency that lies within the passband of the filter, the level of matching is described by a parameter that, of course, we've discussed, return loss. Return loss is the ratio of the power reflected at the input port of a filter, in this case that's terminated at a match load, over the power available to the match source connected to it. Of course, if we have a perfectly matched input impedance at the input of that filter, that the reflected power would be equal to 0. And in that case, the return loss would be a plus infinity. And so the higher the value of the return loss, actually, the better we like it. The less reflected power we have when the return loss has a numeric value that's more and more positive. Now let's introduce another measure that's similar to the return loss, and that is the insertion loss. In insertion loss, we're going to go through and take the ratio of the power absorbed by the match load at the output of our filter to the power delivered by the match source. And so this looks kind of like the power transmission coefficient, but there is a key difference. And the difference here is that in the denominator we have the delivered power of the source and not the available power of the source. Now, to what extent will that delivered power and available power be different? Well, it depends, of course, on the match that that occurs. Since the absorbed power is always going to be less than the delivered power for lossy devices, and again, even we have a very low loss filter, it still has a little bit of loss, we find that this result is going to be a positive value. And we call this value the insertion loss. So the ratio of absorbed power to delivered power will always be a value less than 1, and therefore, if we apply the decimal operator to it, we get a value that is negative. And of course, that's why then we multiply by the value of -1 to make it a positive value. So insertion loss is a positive value. In this case, the lower value of insertion loss is desirable. And again, that is in contrast to the return loss. Return loss, we want a value that is larger numerically, more and more positive. It is a better situation in terms of indicating a better match. But for the insertion loss, we want the value to be low. Ideally, we'd like to have an insertion loss which is 0 dB. Well, what would that mean? That means an insertion loss of 0 dB occurs when the power absorbed by the matched load at the output of the filter is equal to the power delivered by the matched source at its input. In other words, what goes into the filter is the same as what goes out. And that means that there has been no reduction in energy. None of the input power is absorbed. And of course, that would be reflected then into a value of 0 dB. If we have some power that's absorbed inside the filter, the ratio of the absorbed power to the delivered power, then will be something that is less than 1. And the resulting value here then will be a positive value once we multiply it by -1. Typical values we get for insertion loss in filters are maybe half a dB, 0.2 of a dB, a dB or 2. It depends on the filter frequency, center frequencies, and also on the order of the filter. So to summarize what I just said, the insertion loss of a microwave filter ranges, let's say, from about 0.2 of a dB to maybe 3.5 dB, which would be a pretty bad insertion loss. The things that affect the insertion loss are the filter order, and as we get a larger and larger filter order, we have more elements, more opportunity to absorb energy, then the insertion loss will increase, and likewise as the center frequency of the filter, the band over which the passband extends. If we're talking about tens or hundreds of megahertz, typically our insertion loss is lower than if we had a filter bandwidth that extended over gigahertz or tens of gigahertz. So with return loss, if you recall, the denominator has the value of the available power of the source, where in the insertion loss, the denominator uses the value of delivered power. And so how do we relate delivered power to available power? And recall that delivered power is simply the difference between the power available of the source and the power that is ultimately reflected by the input port. The available power is the incident power on the input port of the filter. And so the difference between the incident and reflected power we know is the net power, which must be equal to the power delivered by that source. Once again, if we have a perfect match and none of the power is reflected at the input impedance is perfectly equal, numerically equal to Z0, then the delivered power and available power will be the same. But if there's any kind of reflected power, any slight mismatch at the input port of that filter, we'll find that the delivered power is slightly less than the available power. Again, if the reflected power is small but non-zero. Mathematically, we can go through and we know the reflected power is simply the available power, which is again the incident power on the input port times the input reflection coefficient magnitude squared. Again, this is essentially the load reflection coefficient, but we use the input impedance to calculate the value of gamma. So we can relate the delivered power to the available power with this expression. And again, if we know this, we can then determine the delivered power from knowledge of the available. We could calculate the delivered power, and from that we could then use that in our return loss. Now, again, we could do that, but typically it turns out that we don't. The reason that we don't explicitly determine the delivered power of a match source connected to a filter when we are determining insertion loss is because we assume the filter is well designed and constructed such that the input impedance in the passband is something close to Z0. The return loss is respectable. In other words, the value of the input reflection coefficient is going to be something that's pretty darn small. The input impedance is something close to Z0. And so even though there is a little bit of power reflected, it's not much, and therefore we just make the approximation that the power delivered by our match source is going to be equal to the power available for that quote-unquote match source. And so we sort of make an approximation. We just say that the say that the power transmission function is likewise equal to the ratio of the absorbed power to the delivered power. And from that approximation, then we can express our insertion loss in terms of that power transmission coefficient function. We take that transmission function and we evaluate the center of our passband and apply the decimal operator, multiply by -1, and that becomes our insertion loss. And that's generally how we determine this. Again, this value is not literally the insertion loss because we are taking the ratio then in the denominator for the available power instead of the delivered power, but we assume that those two values are the difference between those two values are so small that it's not worth doing the calculation. And so we use this then as the approximate result. Now let's go back and try to compare and contrast the differences between insertion loss and return loss, and this always causes problems for new students in microwave engineering. The insertion loss provides indication of the power absorbed by the filter internally, and thus not absorbed by the load. So we waste energy by absorbing it internally in the filter, and of course that's a bad thing. We don't want to absorb energy in our filter, and if we have an insertion loss of 0 dB, that would indicate that there is no power absorbed. The larger the insertion loss numerically, the worse it is, the worst case. If we have an insertion loss of 3 dB, that implies that half of the power is lost internally in the filter, that we are taking the available power and burning half of it in the filter, and therefore only half of it will ultimately be delivered to the match load at the other end, for example. So the larger the value of insertion loss, the worse things are. The perfect value is 0. Again, this is in contrast to return loss. Return loss, a numerical value that's bigger, is actually better for us. The worst case is when we have 0 dB. Insertion loss, 0 dB is the ideal case. In return loss, 0 dB is the worst case possible. So that seems kind of strange, and is there some kind of contradiction here? And it turns out there's no contradiction as long as we understand what each of these two values tell us. So the insertion loss is a direct indication of the reduction in the power absorbed by the match load at the output of the filter. And of course, what we want is that power absorbed to be as large as possible. We ideally would like it to be equal to the available power of the source. To the extent that the absorbed power is less than the available power, we find that the insertion loss will increase. So if we have an insertion loss, and this should say insertion loss, not return loss, if the insertion loss is 2 dB, it says the power absorbed by the match filter is, the match load rather, is 2 dB less than it would have been had the filter been lossless. There is a reduction in the absorbed power of 2 dB. On the other hand, the return loss is not a direct indication of the reduction in the absorbed power by the match load due to a mismatch at the input of the filter. And we see that the numerator in the return loss is not the absorbed power. The numerator is the reflected power. In this case, we don't want this numerator to be as large as possible. A higher reflected power would mean then that there's less power that would be delivered to the absorb, a greater mismatch that would happen. We lose power due to reflection. Instead, we want this reflected power to be as small as possible. Ideally, we'd like to have zero reflected power, which indicates a perfect match at the input of our filter, a conjugate match with our quote-unquote match source, so that all the available power is delivered. And so in this case, again, the ideal situation is when the numerator is 0, and that would result in a return loss that would be infinity. So again, this insertion loss is a direct indication of the reduction due to absorbed power. Return loss is more of an indication of how much power is being reflected, and that's why we want the reflected power, of course, to be as small as possible, resulting in a return loss that is numerically as large as possible. So then we might ask ourselves, how do we directly measure the amount of power which has been reduced due to mismatch? Again, return loss is a surrogate that really tells us how good a match we have, but it doesn't tell us directly by how much the power absorbed by the load is reduced due to this mismatch, the way that insertion loss tells us exactly how much power is reduced because of absorption within the filter. So to come up with a measure that would be equivalent to insertion loss, and that it tells us how much power by how much the absorbed power was reduced because of the mismatch, I come up with a term called reflection loss. Again, this is the actual reduction in absorbed power due to the mismatch at the input port of the filter. In this case, it's equal to the ratio of the delivered power of the source to the available power of the source. And again, these two values, delivered and available, will be equal to each other if we have a perfect match. If we don't have a perfect match at the input, though, we'll have some reflected power. The delivered power will be less than the available power. And so that is where the loss occurs. And again, this is a little bit philosophical, this loss, because it's not one where that energy is absorbed anywhere. The loss is really a lost opportunity. We had a source that had an available power of 100 milliwatts, and we only set up our match such that it could deliver only 90 milliwatts. Let's say we've lost 10 milliwatts. Again, not that 10 milliwatts has been absorbed anywhere. It's just that we had the opportunity to deliver it, and it was not not delivered because of that mismatch. So the delivered power, we know, is the difference between the available power and the amount that is reflected. Again, we can see clearly again that if there's no reflected power, then the available power and the delivered power will be equal to each other. If we take the ratio of available power to available power, of course we get 1. The ratio of the input reflected power to the available power is equal, of course, then to the magnitude squared of gamma in. And so this becomes what we call our reflection loss. This would be how much, again, our absorbed power is reduced because of this mismatch at the input port. If we have a well-designed filter, of course, this gamma magnitude squared of gamma in is going to be very small. It's a pretty good match at the input port. And because of that, this value here is going to be something very close to 1. And so the resulting reflection loss that we get is going to be typically something in the tenths or hundredths of a dB. And so because of that, this loss is generally not used in microwave engineering. And really what it tells us is that, if we have a fairly good match at our input port, then we really don't see a reduction in the absorbed power due to that reflection. Most of that reduction in absorbed power will be due to the loss internal to the filter, power that's absorbed and turned into heat by the elements of the filter itself.